When we look at a busy city intersection, a sprawling supply chain, or a transit grid, we call this blur of moving parts a system. We use the word as a shorthand for complexity. In business, the term is applied to almost everything. We talk about economic policies, biological networks, or management techniques to describe large, interconnected webs of activity. But when it comes to software engineering, what exactly is an information system? Historically, the answer was highly tangible. A system was a collection of massive physical machines taking up entire rooms. Or it was a rigid, manual process, running entirely on human effort and neatly ordered rows of metal filing cabinets. Today, our business infrastructure is abstract. We rely on cloud-based networks, virtual servers, and distributed architectures that exist entirely out of sight. Yet beneath that modern complexity, every working system relies on the exact same structural anatomy. Mastering this anatomy from first principles allows us to architect solutions that effectively resolve business problems and scale as those problems evolve. To understand how software should be built, we have to start with a blank canvas. A system is a collection of interrelated components working together toward a common purpose. This flowchart shows the minimum mechanical loop required for any of those components to function. It starts here. Raw data, materials, or signals enter the architecture. That input is then subjected to a specific process. The data undergoes a transformation based on predefined rules. The result of that transformation is the output, the final product or piece of information generated. But the most critical part of this mechanism is not the forward momentum. It is how the system monitors itself. Information about that final output loops back around to the starting point to regulate the next operation. Without this continuous feedback loop, there is no way to adapt to errors. The architecture becomes a rigid, linear sequence that eventually breaks. Of course, that core loop does not exist in a vacuum. It requires strict logical constraints. This diagram shows how we enclose those components by drawing a system boundary. This line establishes a strict limit. It defines exactly what is inside the scope of the project and, critically, what is outside of our control. Everything in that external space is the environment, containing the forces and users acting upon our components. The only places they touch are the interfaces, the designated points where data crosses that line to enter or exit. A mechanism that constantly exchanges data to survive is an open system. If it interacts with nothing, it is a closed system. In practice, perfectly closed environments are incredibly rare. Almost all modern business software operates as an open system, requiring continuous interaction with the outside world. Determining exactly where that boundary lies is an analyst's first task. It dictates the precise scope of what the engineering team actually has to build. If we zoom into the exact center of our boundary, into the transformation process itself, what is it actually made of? Designing an information system requires moving past the technical focus on hardware and compiled code. This chart details the true anatomy. A complete structure requires 5 interlocking pieces. The technical foundation relies on the physical machines and the operating code written to run on them. Then we have the specific information or raw material being collected, stored, and analyzed. The final 2 pieces of this wheel rely entirely on human behavior. These are the individuals operating the tool and the strict rules and workflows they must follow to ensure it works correctly. You can deploy flawless software on the fastest hardware available. If the users ignore the procedures or enter the wrong inputs, the entire mechanism fails. Software engineering is incomplete if it ignores human and procedural components. The architecture must account for the people operating it as rigorously as the servers. How do we construct a 5-part structure like this from scratch? We rely on a formal discipline known as systems analysis and design. This requires a system analyst. They act as the translator, taking ambiguous business goals and converting them into strict technical requirements for the developers. To manage this translation, analysts map the project onto the system development lifecycle. This breaks the engineering process into 4 predictable stages. It starts with analysis and design, understanding user needs and planning architecture before coding. That is followed by implementation and maintenance, building and deploying the software, then continuously monitoring the feedback loop to push updates. The system development lifecycle provides the engineering rigor needed to turn abstract business requirements into predictable, functional machines. The definition of a system is permanent, but the methods we use to build them are continually adapting. In the early days of computing, we built highly deterministic systems. If you entered a specific input, fixed logic guaranteed the exact same output every time. Today, our software operates in probabilistic environments. From financial markets to logistics networks, systems have to navigate massive uncertainty, random variables, and constant fluctuations. To handle this unpredictability, the rigid, linear timeline of the SDLC is increasingly shifting into agile methodologies. The development stages are compressed into a continuous, iterative loop. Analysts now utilize object-oriented modeling, using languages like UML to map out highly complex, intertwined interactions. And the transition to cloud and mobile computing means these architectures must manage distributed access and process vast amounts of real-time data from anywhere in the world. These modern approaches do not abandon the core input-process-output loop. They simply give engineering teams the speed and flexibility to iterate through that loop fast enough to adapt to a probabilistic world. Let's review the architectural model we've constructed. A true information system is a precise mechanism combining hardware, software, data, people, and process. It is enclosed by a strictly defined boundary, interacting with its environment through designated inputs and using closed feedback loops to regulate its outputs. And it is methodically designed and built using the rigorous stages of the system development lifecycle. The next generation of software will heavily integrate machine learning and predictive data analytics. The tools will become increasingly abstract, but mastering systems analysis and design guarantees that no matter how advanced the technology gets, the end product remains a structurally sound tool, engineered to serve its core purpose.